Hello, and thank you for joining us for the final talk of this year's Advances in Battery Research online symposium. I'm George Hammond, Senior Conference Producer at Technology Networks, and I'm here to introduce our final talk of the day, Metal Hydrogen Batteries from Space to Grid-Scale Energy Storage. I'm incredibly pleased to welcome Dr. Majid Keshavarz. Dr. Keshavarz is the Chief Technology Officer at EnerVenue, where he leads the company's product development team. With more than 20 years of renewable energy storage technology leadership experience, Keshavarz has extensive experience in the technical and managerial oversight of research and development activities and the commercialization of electrochemical energy storage and material science. A very warm welcome to you, Majid. Following the presentation, we will also have a Q&A session, and we welcome any questions that you might have. Please ask questions using the Q&A system to the right-hand side of the video player. Now, without further ado, I would like to hand over to Majid to begin his presentation.
Well, thank you for the introduction. I'm Majid Keshavarz, CTO of EnerVenue. EnerVenue is, hold on, all right. EnerVenue is a startup company. We are located in Silicon Valley, in Fremont. Company was founded 2020, 5 years old. We are building metal hydrogen batteries for stationary applications. The technology is based on nickel hydrogen battery that NASA developed back in 70s. It was patented in 1971, used for aerospace for 4 decades. That turned out to be the most reliable battery back then. And then Professor E. Chui of Stanford University revisited the technology at Stanford. Then technology was transferred to EnerVenue back in 2020, and since then we have commercialized the technology for stationary applications. Our mission is to be provider of energy storage for power plants, businesses, and homes. Focus is stationary applications, not portable electronics or EV. The technology is not really suited for that type of applications. The features of this battery is it's very durable as well as being safe. The technology, there's just a brief history of nickel hydrogen battery. It's based on nickel hydroxide and hydrogen electrode. It developed back in 70s and manufactured by Eagle Pitcher, Boeing, Saft companies, and it was deployed for very critical missions like NASA's Space Shuttle, Hubble telescope, Space Telescope, International Space Station, Mars rovers. So there are a lot of data available to public as well on these technology. The question was back then, how come nobody commercialized this technology, outside NASA? And the question was, it's very expensive battery. We did the techno-economic calculations, and it turned out to be about $20,000 per kilowatt hour. Nobody wanted to touch that. It's incredibly expensive. One of the reasons was the material used for this battery, starting with the catalyst, which is extremely expensive. Platinum is used, and platinum today is about $30,000 per kilogram. This battery consists of cathode electrode, nickel hydroxide cathode, and hydrogen electrode, which is catalyzed. Nickel hydroxide cathode is well known. It goes back to 1900s. Nickel iron battery goes back, that's also called Edison battery. Over years, people developed variations, different type of nickel batteries, nickel zinc, nickel cadmium was commercialized in 70s, and nickel metal hydride. Reliable batteries, but they don't last very long. Mainly what they have in common, all of these, is the anode. It degrades, and after 1,000 cycles or so, NASA scientists came up with this new concept that is not really based on typical redox reactions. The anode is actually, in a way, is a regenerative fuel cell. During charge, water is reduced to hydrogen, split water, and during discharge, hydrogen goes back to water. Basically, it's the first step. Charge step is like electrolyzer, and discharge is like hydrogen fuel cell. For this type of reaction, you need a catalyst, and the best catalyst is precious metals. Typically, platinum is the standard, or platinum alloys like platinum, ruthenium, iridium, etc. Still extremely expensive. What we are using today is transition metal-based catalyst. We have developed that and commercialized it. The cost of this catalyst is very low. You're talking about $22 per kilogram versus platinum, which is $30,000 per kilogram. It is low-cost manufacturing and works really well under these conditions. The first thing to test the catalyst is to see the overpotential. We have QC cells to measure the overpotential of both HER, hydrogen evolution reaction, and hydrogen oxidation reaction. As you can see from these graphs, the new catalyst is comparable or even better than platinum under these conditions, lower overpotential, and that's what we are looking for in catalysis. Different C rates, doing really well. The difference is it takes a cycle or two to activate, which is not really a big issue at all. But over time, it gets better and better, as you can see from the plots. These are millivolts, so you're talking about 50 millivolts or so, over potential of both HER and HOR. There are many catalysts reported in literature and academia. They do well in HER, but HOR is a problem. The hydrogen oxidation or recombination back to water. It's always an issue. However, this battery does both steps. It's bifunctional. You don't need two different catalysts for two different reactions. A single reaction works, single catalyst works really well. The next step is whether it's scalable or not. Hundreds of different batteries been made in the lab, in a beaker. However, is it scalable? Can you actually make these things in gigawatt hour scale? And we have scaled this up. It shows our latest pilot line, our line in the for the development for manufacturing of this material. Besides catalyst, we also changed other expensive materials. The next one was separator. NASA used zirconium oxide as a separator. Zirconium oxide is a ceramic, difficult to make, and frankly, there is no manufacturing company in the world who can provide it. A very small company we found in the Midwest, that was the only one. So besides not being able to purchase that, it is very expensive. We have developed a new use a new separator. It's a porous material based on polyolefin, very low cost and suited well for this type of reaction. We also simplified the structural part of the cell. It designed for manufacturing, large-scale manufacturing, for automated manufacturing. Another big piece of the battery is the pressure vessel. Gas-based batteries like this requires a pressure vessel. We generate hydrogen during reaction. We need to contain it and then use it during discharge. So it has to be a leak-free vessel. Very expensive material like used in the past. We have reduced the cost significantly. First two generations, we used stainless steel, and now we switched to composite material, which is very light and low cost. We have developed a DC block for grid applications. Both 1,000 volt and 1,500 volts are available. We also have developed a battery management system, both firmware and software suited for this type of battery, which is very different than lithium ion. The way we charge it, discharge it, it is different. For example, lithium ion, we do CC, CV. In this case, we always use CC, constant current or constant power, charge and discharge, so it's operated differently. And from get-go, we design it so it can be recyclable using non-toxic materials as well, being environmentally responsible. The product evolved over time. The first one we designed and built was 200 watt-hour cell. It was in a canister about 14 inches tall, 4-inch wide. It served the purpose. We built thousands of these vessels, put it in a container, deploy that, and I'll talk about it a little bit more. Then we moved on to 6-foot tall vessel, multiple stacks. That was 1.2 kilowatt hour vessel. It serves well for many applications. And recently, we built a bigger cell, large format, which is 3 kilowatt hour cell. Still 6 feet tall, a little bit wider. It's 6 inches in diameter. We switched from stainless steel to composite material, and we winded in-house, everything done in-house, from cell manufacturing all the way to the vessel winding. A typical charge-discharge voltage profile of this battery looks like this. It is basically nickel hydroxide voltage. It's a shallow, it's not flat. It's got a shallow slope, both charge and discharge. I'm showing 3 traces of 3 different C rates, C over 10, C over 4, and C over 2, with obviously current density dependent. This is a 6-stack cell. So average discharge voltage is about 1.3. That is typical in aqueous-based batteries. It's compared to lithium ion, it's obviously low, but that's how aqueous batteries work. And then it's connected, these things are connected in series to build a voltage. Extensive studies on the C rate suited for stationary applications, C over 12 hours duration all the way to 2 hours at different temperatures. What I'm showing here is from minus 10 degrees C to 45 degrees C at six different C rates. As you can see, under most conditions, the energy efficiency, round trip efficiency is at more than 90%, especially long duration ones. C2, C over 2, C over 4 drops a little bit, but nevertheless, very good performance for this type of batteries. We've done more thermal studies, so looked at real life testing. We build the cells and place them in environmental chambers and program the chambers, trying to mimic, for example, Phoenix, Arizona. The weather got the temperatures from Weather Channel and basically programmed the chambers. The blue trace is the temperature. The low is around 25 and high in this case is 46 Celsius or 114 Fahrenheit. So we are running 2 cycles throughout the day, charge, discharge, and charge, discharge again. One is in the morning, one is in the afternoon. One of them is charged in the peak of the heat, and the result is shown on the right-hand side. It's pretty consistent, very flat performance. Obviously, the morning cycle and afternoon cycle are a little bit different in efficiency, but that's what the utility companies like to see so they can do their calculations, return of investment. This can tell you exactly what they should expect. And most importantly, we are not using any HVAC or anything. This is ambient temperature fluctuating, going high as high as 46 degrees in the afternoon in Phoenix. Then we went to the cold climate, mimicked Denver, Colorado weather during 4 days. The data we got, first day it fluctuates from -6 to 23 degrees C, and then temperature drops all the way to -13. Ran 4 cycles during this weather. It loops. So we ran it for 6 months, 250 cycles. Again, the results you can see it's very impressive. Flat line, you can tell the difference between cycle 1, which is in a warm day, and the third day is the coldest. That's bright red dot, and the other 2 cycles in between, again, very predictable and works well at the -13 degrees C. I should note that technologies like LFP is not recommended even to charge below 0 degrees C. These type of batteries work really well at even cold temperature. The next thing is endurance. This type of batteries are known for their longevity. We built some cells back in 2000, 2001. They're still running. These cells were evolved over time. Small cell 10 amp hour, then 120 amp hour, and 160 amp hour. That's the first generation. We can get 2,000 cycles per year. So that represents almost 4 years of cycling, continuous cycling at C over 2. The small cell is placed in the chamber running at 45 degrees C. We can see the very little degradation, and the other 2 are at room temperature, and we can see 1 or 2% loss in capacity over almost 7,000 to 8,000 cycles. That shows that the catalyst is working well and getting data similar to what we expected to be able to run thousands of cycles over time. They're still running, so we'll see when actually they degrade and get to the 80% of its capacity, how many years it takes. Since we cannot wait 30 years, it takes 30 years, 3 cycles a day to get to 30,000 cycles. And that's a long time, and we cannot obviously wait, and the company is not that old. One of the things that we did accelerated test, we ran the battery at top of the charge. Typically batteries are stressed at top of the charge. We run at 95%, 100% continuously. We have collected about 80,000 cycles, and they're running, still running, and very little degradation we see. We also compare it with where battery is more comfortable in the middle of the SOC 50 to 55. There's not much difference, really significant difference we see, which is very unusual. Usually, typically, other batteries, top of the charge, you see degradation much, much faster. So the way we check this state of health, every 500 cycle, we do a full cycle, 0 to 100%, and look at the capacity, voltage, etc. And what we are seeing now after 80,000 cycles, we're losing about 3.5% in capacity, and the round trip efficiency drops 3 to 5%. And this is very encouraging results that we are seeing here from this type of battery. We're doing it at different temperatures, different conditions, but this is representative of one of the accelerated tests. We went even further to conduct some other accelerated tests. We ran the battery at 60 degrees C, at 5C charge, 5C discharge, 100% depth of discharge. So 0 to 100, going back and forth at 60 degrees C. At the same time, under same conditions, we picked 2 types of lithium-ion batteries, one NCA from Panasonic and one LFP. From the graph, it is clear that NCA reaches 80% of its initial capacity after 70 cycles, the green dots. LFP did much better. It lasts 600 cycles. It takes 600 cycles to get to 80% of its capacity. We ran it for 2,000 cycles, and EnerVenue battery as well, and we see that only losing 5% of its capacity after 2,000 cycles, whereas LFP reached 15% or so. Very different behavior. This is why this type of batteries are known to be very durable and basically can handle harsh conditions, hot and cold. So from safety point of view, that's another feature that is required for power plants and utility applications, because these are really deployed in gigawatt hour or 500 megawatt hour, etc. Fire, it is explosion, etc. It is extremely important for this type of applications. So we send these batteries to a third party for a number of different tests, safety tests, which I will share a few of them with you. Went through overcharge, flammability, thermal runaway, nail penetration, etc. So the very first one, and common test, which is usually used for lithium ion as well, and there you can see the videos, find videos of lithium ion on Google, YouTube. You penetrate a nail, it ignites and explodes, and you see the flames coming out of the battery, like the one pictures I've shown on the left-hand side. We repeated the same thing with our battery. We just had to use a bigger nail and basically pierce through by force The result was very encouraging, actually very good results. No fire was observed. It just vented the gas. Every experiment that I'm talking about, these are at 100% charge. 100% charge is where that is pressurized with hydrogen, and this same hydrogen, the hydrogen is consumed during the discharge. However, all these tests are at top of the charge. Similar experiment was conducted, and with in this time the vessel was shot by 7mm Remington Magnum from a distance 40 feet away. Projectile actually pierced the vessel, but did not exit. But the point is, there was no explosion, no fire or anything. Simply, it was just degassed. That was also very good result we got from these tests. Thermal runaway, always an issue with lithium ion, other type of batteries. This time, the vessel was wrapped with heating elements. Temperature reached 320 degrees C, and then vented. But no fire, no explosion or anything, unlike lithium ion, which we see typically, it breaks down around 200 degrees C. Overcharge, very important. The battery was overcharged, two different conditions, 40 amp C/4 and C/2. It got to a point that temperature reaches, when you overcharge this, obviously that you generate heat, current has to go somewhere, reach around 200 degrees or so, but then no fire was again seen, or explosion or anything. It just got hot, released the gas. There is a safety valve in this batteries, as is shown or in a bracket here on the right hand side. It at certain temperature and pressure releases the gas. I should point out that lithium ion typically set on fire around when SOC gets around 116% or so. These are charged up to 160%, and in one other case, 200 degree state of charge. My favorite one is when you place battery on a bonfire at 100% state of charge. Again, it heats up, pressure builds up, but at some point releases the pressure. What's interesting in this case, you still have flame around, but you don't see propagation or flame. It basically, what exits is the gas that is non-flammable. It means at this point, water is converted to steam, and with a little bit of hydrogen left, perhaps. It's most likely less than 4%. That is not flammable. It's mainly steam. So going through all these tests that I shared with you, only a few of them, our product is licensed, it's certified, UL 9540A. That is our battery, the second generation battery, and we are currently certifying our latest design, which refers to 4.0 design. It's on, the difference is it's a larger format battery, but fundamentally it's the same battery. So as pressure vessels or cells evolved, the DC block also evolved. The first deployments were based on the first generation we call IPV, individual pressure vessel, and then the second generation, we also smaller containers, and now we are deploying our fourth generation vessels and DC blocks. We have deployed these batteries all over the world, including many states, different parts of the US, and also internationally, Australia, Germany, Denmark, South America, Middle East, etc. So far, the results are very good in the field, different climates, different applications. The customers are very pleased with the performance of this battery. One of the first customers was Duke Energy, North Carolina, Enel in Colorado, and we used also Schlumberger, who are one of our investors as well in Texas. Duke Energy been a great partner for us. One of the biggest utility companies in the U.S., covers East Coast, North Carolina, all the way to Florida. They have programs for solar plus storage, microgrid, off-grid, grid tied, etc. Been very helpful and to test these and learn from field data and to improve our batteries. Very good partners. We are very happy to work with Duke Energy. This is the spec sheet of the new pressure vessel. It's a 3 kilowatt hour, 137 amp hour, 1500 watt nominal power. It's C/2 to C/12. That's typically the case in our and PMS. We have two types: 1000 volts, 1500 volts as well, certified. So the new racks for sale are based on the new design 3 kilowatt hour. We put 50 of them in a rack, and we're getting really good feedback from the customers. These racks are they come with a BMS as well as BMI, and for also certifications. It's very simple. You can use cranes or forklift to move it around. The DC block it's in the front, accessible. We have 2 fans in the bottom, and we use forced air. There is no HVAC. HVAC is not required for this battery, and the air exits on the top to basically remove the heat. Scalable, stackable structure. These containers can be stacked, so you can form a cluster. We don't sell vessel or single rack. It's really the clusters are multi-megawatt hours. So 6 of them together, that gives you 900 kilowatt hour, and then 18 of them, that's 2.7 megawatt hour. This is what customers are asking for. They want a simple installation, plug and play, fast installation for grid application. They don't want to pay for labors in the field. So the simpler, the better. And that's why we have learned over time to simplify these and make sure we transfer something that is in the field, we can be assembled very, very quickly. The new concept that we're working on it's a warehouse-based solution. Basically, similar concept, stripped down rack, energy rack again. However, you can stack them up 3 layers, 4 layers or so in a warehouse. So it can be, it's more effective for the space. It is more cost effective. It can be temperature can be controlled, and easy to assemble these things. It takes about 1 acre to basically put 400 megawatt hour of battery together. Um, Again, that's what customers want, and the all connections, etc., are up in front. It's easy to connect them together, and it comes with BMS and the wiring. In the end, I would like to just say the attributes of this battery is very clear. It's its life cycle. It's the most durable battery designed. It is safe, also very flexible from operational point of view. It is proven technology, again, at 4 decades at NASA, and by our deployment so far, and the return of the investment is very clear. The techno-economic calculations always favor this type of battery. At the end, I would like to thank everyone for your attention.
Thank you, Majid, for that fantastic talk. We really do appreciate you sharing your expertise with us today. I can see that we do have some fantastic questions from our audience already, so let's move straight onto the Q&A now. So Majid, your first question is, what modifications to NASA's original design were required to maintain performance when switching to EnerVenue's commercialized concept? And how did you address any potential catalytic activity differences?
Yes, very good question. Catalytic activity is extremely important, and we spend a lot of time. Before the company was formed, by the way, I spent a year in incubator, accelerator, it's called Inotech, working on that, affiliated with Stanford. Our effort was really just working on the catalyst. And two reasons, whether activities and scalability. So that was our focus, and the results were very positive. That's why the company was founded. As I mentioned, overpotential measurements, cycling at different conditions, and how do you manufacture it? If it's complicated vacuum technique requires, none of that would work for commercialization, especially these days. The cost of batteries have dropped dramatically. You have to be able to compete with lithium ion. This is a very simple manufacturing process. It's electroplating technology that's been known for centuries. The capex is low, and opex is very, very simple.
That's a fantastic answer. Thank you so much, Majid. Now we have a question from a member of our audience. They mentioned that there was a power plant that was near Monterey that had a battery storage fire, but they were wondering how EnerVenue's containers can handle a fire and if they are able to sort of propagate from container to container. I was wondering if you could perhaps elaborate on the safety aspects a little more.
Absolutely. This is the key here. That's why this propagation matters. There are a lot of tests done, right? You overcharge, for example, two of the vessels in a container and see if there's a thermal runaway and if it propagates to the next cell, etc. We have UL examiners actually working with us, looking at these things. And we don't see that in this battery. As I mentioned and shared some of the data with you, one thing is built in this battery is when you have fire, it is hermetically sealed, and it heats up, and it shorts the battery. When it shorts, it heats up itself, but it consumes the flammable hydrogen. Therefore, it does not propagate and releases basically steam. Done this test many times. It's actually hard. It is very, very interesting feature of this battery. That's why it is suited for that type of applications, the stationary application, especially when you have megawatt hour, gigawatt hour connected to each other in a huge fashion rather than small batteries that we use daily.
That's another fantastic answer. Thank you so much, Majid.
Mm-hmm.
Now we have another interesting question from a member of our audience. This technology certainly seems to be an incredible, great step forward for the future of energy storage. They were wondering, obviously you mentioned throughout your presentation, you have many clients who have opted for your batteries and seen great success.
Mm-hmm.
But I wonder if perhaps you have received any potential orders from universities looking to perhaps use your technology.
No, we obviously work with Professor Chui of Stanford, but no, we have not received any requests from any university.
Wonderful. Not a problem at all. Thank you so much, Majid. Now, moving on to the next question. Where would you say this technology is most applicable in today's society, and where do you see it evolving in the next decade?
Utility. I really think the grid is getting old. It is old in US and most countries, and it is very expensive to upgrade it. The best thing is distributed energy. We have solars everywhere. The cost of solar has dropped significantly, and what's missing is energy storage. But energy storage that is safe and complements solar. Solar right now, panels are warranted for 25 years, 30 years. So you need a battery that lasts that long too. And that's where this technology shines. I also want to be able to cycle it a few times a day, at least, and not limited by number of cycles. Again, that's one of the features of this battery. So where I see it, it's first utility, and for the utility scale off grid and grid type applications. Both of them, I think this technology is suited for.
That's fantastic. Thank you, Majid. We have time for a few more questions today before we close out this session
Sure.
and the event.
Sure.
So moving on to your next question quickly, is there any special types of separator that are required for this chemistry? For example, ion selective membranes?
Excellent question. Very good question. No, the answer is no. I used to work on flow batteries myself for many years, and that technology requires ion selected separators or membrane. This is a very simple porous material. However, it has to be hydrophilic enough so it can basically act as reservoir for electrolyte. This is not a flooded battery, by the way. Maybe I did not mention that. This is the vessel is not filled with electrolyte. You just have enough electrolyte for that is required for the reaction. So separator has two functions: separating cathode from anode, prevent shorts, as well as acting as a reservoir for electrolyte. So it has to be and it has to be hydrophilic, since the electrolyte is basically salt water. And the cost, I must mention, the cost is very low. It's probably one of the lowest costs I've seen. We're talking about $1 per square meter. Can't get lower than that. Did I answer your question? Hello? Can you hear me? George? Hello? Hello? I think I lost you somehow. Hello? Don't know exactly what happened. Can you turn on the audio? Can you hear me? Hello?
Hello, Majid. Can you hear me now?
Yes, what happened? Sorry, is it my
Wonderful.
side or?
No, apologies. I believe that was my end. Apologies, everyone. Anyway, we do have time for one final question just before we close out this session. And it was a great question from our audience, which is a very interesting question, actually. Are there any, just thinking of scalability, are there any plans for any different shapes and storage sizes for your batteries?
Very good question. Yes, yes, absolutely. There are many other shapes that we are investigating. You can think of a barrel shape, for example. You can think of separating the hydrogen storage tanks from the stacks, etc. I have written a few patents actually on those. But right now, the focus is these long cylinders.
That is wonderful. Thank you so much, Majid. Unfortunately, that is all that we have time for today. Apologies again to our audience for the issues with the connectivity at the end there. Just a reminder to our audience that any questions that we didn't have time to get to will be answered offline as soon as possible. So that's it for this year's Advances in Battery Research 2025 online symposium. As mentioned throughout the day, all the talks from today's event will be made available to view on demand for the next 30 days. And you can access the talks via the same link you used to access them today, and we'll be sure to pass on any further questions you submit through the system to the relevant speaker. So that just leaves me to say a massive thank you once again to Majid. Thank you so much for your presentation, and we will see you all again soon at our next online symposium, Cell and Gene Therapy 2025. Thank you once again, and goodbye.
Thank you so much. Bye.